Usually you think of blue as a cold color and red as a hot color, but it's the other way around. Okay, so the shorter the wavelength, the more energy it's got, and therefore it's hotter. Okay, and the reason for this is the way that the black body wavelength. I'll show you a slide in a sec here. But the way the black body works out, as you get hotter and hotter, you not only radiate more stuff, but you shift toward the blue side, right? So this is how the formula is given in your data packet. They give you lambda max, and then they tell you that it's meters. And then here's this constant, right? And then T, they even tell you Kelvin. Isn't that nice? You know, lest you forget and put Celsius in there, right? Although for a star with a temperature of thousands of degrees, forgetting that doesn't make that big a difference. You don't want to say that, right? So this, I scanned this out of J. Pasakov's Contemporary Astronomy. These are black body curves. We're only looking at the part that Planck didn't have troubles with, right? This part here is cut off. But notice that as the stars, this is a star that's at 0 Celsius, a very cold star, right? There we go, right? This is a Minnesota star. But even 273 is not 0 kelvins, right? Okay, so it's radiating heat. Here's 600, 1,000, right? I think 1,000 is like glowing. Actually, we can tell its peak is right here. And so 6,000 angstroms. An angstrom is 10 to the minus 10th. So this is 600 nanometers. Yeah? We can see that, right? So this guy here, this 1,000, is actually emitting stuff, a lot of stuff that we can see. It's going to glow red hot. And then 2,000 is definitely going to be glowing pretty like white hot, right? It's going to be pretty much in the center of our, this is 200 nanometers. So this guy's peak is right in there. Notice that the peaks of these guys fall in a very predictable place. You see that? And this is the straight line. So basically that formula is just the formula of a straight line, isn't it? And then those peaks lie on there. So notice that not only does it get higher, but it also gets shorter, right? So 6,000 degrees is a bluish sort of color, right? The peak is shifted to blue. So put that in your notes. A star has a surface temperature of 5,787 kelvins. What is its lambda max? What's its peak black body? Doesn't this imply that if you look at the spectrum of light from a star, the black body radiation, the heat given off by the star, right, that you can predict its temperature? Isn't that what it predicts? I'm thinking so, right? Okay. So what's our formula? It's 2.90 times 10. It's 2.90 times 10 to the minus third meters per Kelvin, right, over the temperature. So this is going to be, this is pretty tough, okay? Pretty tough stuff here. And then we're going to divide by 5,787 kelvins. I don't think it's meters per Kelvin, it's meters kelvins, isn't it? Because these guys are going to cancel and we're going to get with meters. That's on your note guide. See how it says meters per Kelvin? That's wrong. It's meters Kelvin, just like it says in the slideshow. And then this is, we can do it, 2.9 e minus 3 divided by 5,787. And this is equal to 5.011 times 10 to the minus 7th meters, which is 501 nanometers. Yeah? What can we see with our eyes? Can't we see about 400 to 700? Yeah? So this falls nicely in the middle of there, right? I think this is the temperature of the sun, roughly. Okay? So about 501 nanometers, and so it's nicely in the middle. I think it's a little toward the short end, right? Okay, so this is blue or violet, right? This is This is going to be red, right? That's kind of right in there. Whiteboard. Let's try whiteboard. We don't want to do too many whiteboards. We want to do just the right number of whiteboards.
Yeah, whiteboards can never be too many jelly beans.
You can't have too many jelly beans.
Yes, I know. I really want one. I'm actually a little bit upset that the assembly was canceled. Yeah, the sole purpose of.
The sole purpose of
I want
je vais suivre Je vais suivre le cours de IB Physics 2. Yeah. Hey, give me some units there. Huh? Oui, oui, mademoiselle. I don't even know how to spell anything in French. I'm just listening to it. Yeah.
That's right.
Is that right?
They scored their
I have no idea. Horses' ovaries, that's right.
What?
Spell horses' ovaries.
We should watch more of Llama's Hat for that.
Friday song.
That's right.
It is Friday.
It is Friday.
Oh.
Vendredi.
Why is there a dead human in here? You watched those, didn't you?
We saw part of one, yeah.
Well, we should watch all of them. 'Cause
That's
they're
right.
all really fun. And they're pretty short.
I like the last one.
They're all.
How about salad fingers? You ever seen that?
Oh, that's great.
And we need to watch our Friday song. Spoon.
I like to touch rusty spoon. That's right. Huh?
Usually everything's over here.
Yeah, he sticks the kid in the in the oven. Then you get, and there's some like dead body, and he sticks it on a hook, and that's nice.
Yeah.
That's not disturbing.
Dead or anything.
Yeah.
Just a little.
No, I don't get any.
So this is, I think the temperature is going to be 2.90 E minus 3 meters Kelvin divided by 940 E minus 9, right? This is a cold star. Oh, hey, that's enough of those. All right. Concept 0. I guess that other one was concept -1. Okay. Now if we can figure out the temperature, which we can figure out from the wavelength of light, right? We can figure out temperature. We can then figure out the luminosity. And the luminosity, there's two ways to figure it out. One way is to calculate it using this formula. But if you have a really, really good telescope, you can actually zoom way, way, way in on a star, and there's actually writing on the star, just like a light bulb. And it'll say, 5.6 times 10 to the 26th watts or something like that, just like light bulbs. Okay. But most stars are too far away to actually see the writing on them. Okay. In fact, all of them are except for the sun. Okay. So what we have to do is actually use like science and stuff like that, right? Okay. So this is the actual power output in watts, right? Here we go. Okay. And there's a formula here. This is the Stefan Boltzmann constant. Okay. And you have to pronounce that correctly, right? And then it's temperature to the fourth. So that's a crazy thing. And they love, love, love. In fact, I have not seen a paper 3 for the IB physics test where they don't have you do some calculation with this. So, it's to the fourth power, right? It's crazy to the fourth power. Okay. Stars are spheres, or we're going to assume they're spheres. So this is always pi r squared, 4 pi r squared. Sorry.